the figure below is a rectangular loop of dimensions 20 centimeters by 30 centimeters. The loop is partly filled with magnetic field whose strength is 1/4 Tesla and is directed into the page. The loop has a resistance of 3 ohms. You grab the loop and pull it to the right with a constant speed of 0.4 meter per second. We are to find which way the current flows in the loop, what is the voltage generated in the loop, the current, and finally how much force is required to maintain the motion at 0.4 meter per second. We recognize that this problem is an application of Faraday's law, and we've written Faraday's law in 2 forms. If we have a single loop, the voltage generated around that loop is negative the time derivative of the magnetic flux through the loop. And if we were instead to have a coil, since a coil is simply a series of loops, the total voltage generated across this series combination is n times the voltage of any single loop. In the problem at hand, we only have a single loop, and so we'll be using the first of these 2 formulations. The first question we're asked regards the direction of the current induced in the loop. Now, although Faraday's law is complete and is correct and will tell you the appropriate direction, it is somewhat complicated in that there are many possibilities to slip up in minus signs as you formulate the answer. For this reason, we will use Lenz Law, which states that at the end of the day, the full effect of Faraday's law is to oppose the change in any magnetic flux. Effectively, the opposition to change is found in the minus sign of Faraday's law. Let's examine our loop carefully, and as we do so, we recognize that the loop is not entirely filled with magnetic flux. Only the portion indicated here by the diagonal blue lines is actually filled with magnetic flux. The rest of the loop is empty. As we pull the loop with some velocity to the right, the region containing the magnetic field becomes smaller and smaller. Therefore, we effectively have a change which can be summarized as less flux into the screen. If we should have less flux into the screen, we ask ourselves what positive action the loop could take in order to oppose this change. And the answer is simple. The loop will make some current to drive new flux into the screen. In this way, the loop attempts to compensate for the lost flux due to the motion by generating brand new flux. We determine the direction of magnetic field and therefore magnetic flux by using our right hand and curling the fingers on our right hand. We recognize that the curled fingers represent the current and the thumb represents the magnetic field. And we attempt to direct the thumb into the screen. And when doing so, we'll find the answer to part A, that our fingers curl in the clockwise direction, and that is therefore the direction of the current that has been induced in the loop. For part B, we should solve Faraday's law directly, and we're going to need to begin by specifying what is the magnetic flux through the loop. Flux is always field times area, and since the field is a constant strength, we'll be able to simply write this as B times A. The area in question for this calculation is that given by the hashed lines in the diagram. The vertical extent of this area we will call L2 in order to specify that we mean the length, which is the 20 centimeter side, as opposed to L3, which is the 30 centimeter slide. The other side of the magnetic flux area has a variable length because as the loop moves, this becomes smaller and smaller. We're going to call that distance x temporarily, and so we can see that the area in question is L2 times x. This expression we can now take the time derivative of, noticing that b and L2 are constants and will come out, and finally that we have a name for the derivative of position with respect to time, and that is velocity. We are therefore able to plug in the values, yielding a result of negative 0.02 volts. As always with Faraday's law, we have to be very careful about what positive or negative means in terms of this result. It is in fact part A of this problem that tells us that the negative sign means clockwise for the direction of the current. In the next part of the calculation, we recognize that this voltage of 0.02 volts has been applied to a loop of wire with a finite resistance. And Ohm's law will tell us the relationship between the applied voltage and the induced current in this loop. Solving Ohm's law for the current and plugging in the values, we come up with an amount of current 0066 bar. Please note that I have been somewhat cavalier with the sign of the current. As in the previous part, the sign of the current is only meaningful when you put it into a term clockwise or counterclockwise, and that's what we solved for in part A. Since the voltage is in the clockwise direction, so is the current. Finally, in part D of the problem, we need to go back to the figure to understand why there is a force on the loop overall. The clockwise current means that the current will be directed as given by these small arrows. Whenever you have a current in a magnetic field, there will be a force on that piece of current, and the direction of the force will be given by the right-hand rule. If we apply the right-hand rule to this problem, we will find that the piece of wire on the left has a force to the left, the piece of wire on the top has a force upward, the piece of wire on the bottom has a force downward, and the piece of wire on the right has no force because that piece of wire is outside of the magnetic field. Although the upward and downward forces happen to be equal and opposite and therefore cancel, the left force is not balanced by a right-hand force, and therefore the net force of the wire is that comes from the left-hand edge, due only to the piece of wire on the left-hand edge. Therefore, in our force formula that tells us the force is ILB, our net force is going to use the length L2, meaning that the length L3 was in fact entirely irrelevant to the whole problem. Think about that for a moment and you'll see that it must be true. So let's simply plug in a few numbers and finish this calculation. Given a current of 0066, the length L2 of 20 centimeters, and a magnetic field of 1/4 Tesla, we find that the net force required to maintain the motion of the loop is 3.33 times 10 to the minus 4 newtons. It's interesting to note one aspect about this force. Going back to the original diagram, we see that the force in question is directed to the left. And going back to our friend Lenz Law, we recognize that Lenz Law says oppose change. The change is that you're moving the loop to the right. The opposition to this change is generated by a force to the left.